In this final video, we are going to identify which schemes come from varieties over K. We have already done most of the work by saying that the pre-varieties over K sit inside the schemes as the reduced finite type schemes over this field K that we work with. And so the last property that we need is to say when is a scheme separated. And in fact, this is again one of these relative notions. So somehow you say that X is a scheme over some other scheme Y, and then you will define what it means to be separated over Y. To do that, we want to have this diagonal morphism. So we say the diagonal morphism is the morphism from X to X cross over Y with X. And it is the morphism induced by the identity in the two factors from the universal property here. So, I mean, if you recall, the standard diagonal just sends X to X comma X. And goes from here to the product of X with itself. And now we take this fiber product of X with itself over Y. And again, just take kind of 2 times the identity. And so what does it mean to have this induced by the universal property? Well, the universal property for this fiber product here, this diagram, is saying whenever you have any space here, let's take X, and you have 2 morphisms here and here, let's take 2 times the identity, such that the maps to Y are the same, which in this case is automatic because kind of this path and this path just give the same morphism. Then you find a unique morphism of schemes from this space to the fiber product. So take that one here. So we exactly apply this universal property and get this diagonal morphism. And then we define X to be separated over Y if this diagonal morphism is a closed embedding. So this we defined already. This just means that locally on an affine cover, it looks like this spec of R modulo J going to spec R. In this case, actually, we won't really need this or prove this, but in this case, in fact, this is equivalent to saying that the image of this morphism here is a closed subset, just on the level of sets, is a closed subset of this fiber product. So in this case, this would be enough. And then as a reward for going through these definitions, we now have this proposition here, which says if K is an algebraically closed field, then there is a bijection between the varieties over K and these schemes which have this whole laundry list of properties, namely they're now separated, they're over K, they're reduced, they have no nilpotent functions, and they are finite type over K. And this bijection just sends X to this X scheme. This also induces a bijection on the morphism. So if you have X and Y, 2 varieties over K, then the morphisms between them as varieties are the same things as the morphisms between their schemes, their associated schemes. And here you need to take morphisms of schemes over K, as we're going to see as the last thing in the video. So yes, so this means you can basically understand everything about these varieties and the maps between them inside this language of schemes. And so why did we go through all of this work? Well, it's because now we can identify varieties with their respective schemes. So instead of me, for the rest of the course, always saying, this is the scheme associated to this variety, we just identify now any variety with its scheme. So somehow in the last part of the course, when I say variety, I just mean a separated reduced scheme of finite type over this field that we work with. When we say points of a variety, we mean exactly these closed points associated to these irreducible 1-element sets inside this X scheme. And when we say morphism of varieties, we just mean morphisms of schemes over K. Okay, because this then allows us to basically use all the properties that we showed for the varieties. We continue to use them for the associated schemes, but now we have this additional language that we can work with. Okay, and so as an example of this, now with this convention, I can just write an over k is the spectrum of this. Before, I would always have to write scheme associated to an over k is the spectrum. And from now on, well, let's just spare ourselves this effort and just say an over k is the spectrum. And some, I mean, many modern algebraic geometry texts would even kind of define an over k as the spectrum, and just move on from there. I mean, you have the option to skip this entire theory of varieties and just go straight for the theory of schemes. And we kind of took a more gradual route and first worked through this theory of varieties, and now just at the end talk a bit about the schemes. And then this final warning that I mentioned is that it's really important in this context to make sure that the morphisms of these schemes here are morphisms over the field K. And we can see this in a particular example. So let's take here for K the complex numbers. And then, so somehow here, this ring here is this polynomial ring in over the complex numbers in these n variables. So as purely as rings, there is a ring homomorphism between them, which takes a polynomial and then just has the image of this polynomial be the same polynomial where you just take complex conjugation over each of the coefficients. So like, for example, the polynomial x plus I would go to the polynomial x minus I. And you can check just as the complex conjugation is a ring homomorphism from complex numbers to itself. In fact, this thing here is still a ring homomorphism. But it is not a homomorphism of C algebras, because the problem is, so the complex numbers map to the two sides here as the inclusion of the constant polynomials. But this doesn't give a commutative diagram, because if here you have the complex number I, it maps to I, and then here it maps to minus I, which is not the same thing as I mapping to I here. So this diagram doesn't commute. It's not a C algebra morphism. And so there is a corresponding map of schemes. This goes from kind of the scheme here to the scheme here, which is induced by phi. This exists as a scheme morphism, but not as a morphism of varieties. So somehow, because again, somehow now on the level of schemes, if you have spec C here, these two things map to spec C, but this would not be a commutative diagram of schemes. So it wouldn't be a morphism of schemes over spec C. In fact, this morphism here, induced by this complex conjugation, so somehow this morphism is the complex conjugation morphism. So somehow it takes this n tuple of element and sends it to the complex conjugated element here. And we know that this is not a morphism of affine varieties over C as we allow it. Because, well, these should be given by polynomials, as we know, but the polynomials with coefficients over the complex numbers, but we know that the morphism x is sent to x bar is not given by such a polynomial. Okay, so this is something that we don't allow. We want to have always the base field C being constant, not changing in these morphisms here. So that's the last thing we wanted to do about schemes. And now in the remainder of the course, we are going to look at a bit more of extra structure on these schemes, which will in the end allow us to answer a few more questions, even some questions that we're interested in, which just concern the language of varieties.